Have you ever found yourself wondering what is actually going on under the hood of an AI? How does it go from looking at a bunch of random data to making these incredibly smart predictions? Well, it turns out it's all about math. So today, we're going to go on a little mathematical quest to find the engine that really powers almost all of machine learning. So yeah, the big question is, how does a machine really learn? It's definitely not magic. And it's not about becoming self-aware or anything like you see in the movies. At its very heart, it's an incredibly elegant mathematical process. And you can really think of that whole process as a quest. It's a journey with one single very clear goal, to find the point of the lowest possible error, to be as right as it can possibly be. Okay, so let's start with the first part of our journey. We need to define the goal. For pretty much any machine learning model, that goal is always going to be the same. Find the minimum. I want you to imagine that for every possible setting of our AI model, we can calculate some kind of error score. A high score means the model is making bad predictions. A low score means it's making good ones. Well, if you were to plot out all of those possible scores, you'd get this complex, rolling landscape of hills and valleys. The entire process we call training an AI is really just an algorithm trying to find the lowest point, the very bottom of the deepest valley in this huge imaginary landscape. But, before we can start walking through that landscape, we need a language to even describe it. We need a way to map the terrain. And in the world of machine learning, that language is built on two things: vectors and matrices. So first up, we have the vector. And honestly, it's just a fancy name for an ordered list of numbers. Think of it like a set of coordinates. It can represent a single data point, like, say, all the pixel values in one image. But, and this is crucial for our quest, it can also represent our current location in that error landscape. It is our "you are here" marker on the map. Okay, so what happens if you stack a bunch of those vectors together? Well, you get a matrix, a big rectangular grid of numbers, and this is how we organize everything. A matrix can hold our entire data set, where each row is a single data point, or it can hold all the internal knobs and dials of the AI model itself. We call these the model's parameters, and they're what the AI is going to be adjusting to try and get better. All right, so we have our map. We know our goal is to get to the lowest point. The next logical question is, which way do we go? For that, we're going to need a compass. And our mathematical compass is something called the derivative. And this is the real problem, right? On a simple, straight, flat slope, it's pretty obvious which way is down. But on a complex, constantly changing curve like our air landscape, the downhill direction changes at every single step. So how do you figure it out? Well, let's start by just picking 2 points on the curve and drawing a straight line between them. The slope of that line, it gives us a kind of rough idea of the steepness, but it's not super accurate. It's really just an average over a pretty long distance. But watch what happens as we slide those 2 points closer and closer together. See that? The line starts to hug the curve. The slope of this line becomes a much, much better approximation of how steep the curve actually is right in that specific spot. And if we take this idea to its logical extreme, bringing the points infinitely close until they're basically the exact same point, the line now just barely kisses the curve at that one single spot. This is what we call the tangent line. And that right there brings us to the definition. The derivative is simply the slope of that tangent line. It's no longer an average slope over some distance, it's the instantaneous slope. It gives us a precise measurement of how steep the hill is right under our feet at this exact moment. So how does this work as a compass? It's actually pretty simple. If we're standing on the left side of a valley, the slope is negative. It's telling us the way is downhill. If we're on the right side, the slope is positive. It's pointing uphill. And right at the very bottom, that perfect minimum we're searching for, the ground is completely flat. The slope, our derivative, is exactly 0. Now, a single derivative is the perfect compass for a simple 2D curve, but our real error landscape, it is far, far more complex. To navigate that, we're going to need a much more powerful guide, the gradient. And here's why we need it. Real-world models aren't just adjusting 1 or 2 parameters. They're adjusting thousands, sometimes millions of them at once. And that means our landscape doesn't have just 2 dimensions, it has millions of dimensions. We can't even visualize that. But the amazing thing is, the math still works. To handle this complexity, we start with a concept called the partial derivative. It's like asking a simpler question. If I only tweak this one single parameter, just a tiny bit, and hold everything else steady, how much does my error score change? We do this for every single direction or parameter one by one.
The gradient is what you get when you do that for every single dimension, and then you bundle all of those answers together into a single vector. It's the ultimate compass. It combines all the individual slopes from every direction into one master vector that tells us the overall direction of the steepest slope in our crazy high-dimensional space.
Now, here is the crucial insight, the whole secret. The gradient has this one fascinating property. It always points in the direction of the steepest uphill climb. And, well, if we know the fastest way up the mountain, then we also know the fastest way down. We just have to go in the exact opposite direction.
And that right there brings us to the solution of our quest, an algorithm called gradient descent. And it's just beautiful in its simplicity. You start somewhere random on that error landscape, you calculate the gradient to find the direction of steepest uphill, you take one small step in the exact opposite direction, and then you just do it again. Repeat, over and over. Step by step, you're just walking down the hill.
And that's pretty much it, this simple, powerful, iterative process of just following the negative gradient. That is the fundamental engine that drives the training for so many of the AI and machine learning models that we use every single day. From a simple prediction model to a huge, complex neural network, at the end of the day, it's all a quest for the minimum. But this does leave us with one final fascinating question. Gradient descent is great at finding the bottom of whatever valley you're already in. But what happens when the landscape has millions of dimensions, with countless hidden valleys, and some of them are much, much deeper than others? How do you make sure you've found the true global minimum and not just a small local one? That question, and the search for its answer, that's one of the biggest challenges in the entire field of artificial intelligence today.